You are listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute at your desk or wherever you might be with the Worth Electronic What's Up podcast. Now, today's podcast comes directly from a recent webinar presented by Worth Electronics' own George Slama. George is a senior application and content engineer with many years of experience. This webinar is the first of a two-part series that covers the basics of magnetics used in switch mode power supplies. The first session covers inductors, and the second session covers transformers. There's a huge range of inductors that are used in a wide variety of topologies: buck, boost, and the list goes on. But how do you go about specifying and selecting the right one? Well, in this presentation, George covers the influence of core materials, the difference between saturation current and rated current, the effects of frequency and temperature. You'll gain an understanding on when to use an inductor as a storage device and when to use it as an impedance device. You'll also learn how is energy stored and what are the effects of gaps. George then wraps up the session with the special multi-winding inductor, commonly referred to as the Flyback transformer. So enjoy this presentation of Basics of Power Inductors with George Slama.
Today I want to speak about the basics of power inductors used in switch mode power supplies. The main topics are outlined here. Why are inductors important? A quick review of the laws governing magnetics, a little about the core materials and their characteristics since they have a major influence on the performance, how energy storage works, and how inductors work in inverters, what are the main specifications to get right when choosing an inductor, and this session wouldn't be complete without coupled inductors and this thing we call a flyback transformer. What's so important about inductors? Let's take your mobile phone, for example. Inside are two main parts. One is the battery, which provides the energy to power the phone. Typically, it's a lithium-ion battery, where because of the chemistry, the voltage is about 3.7 volts. With batteries, the higher the voltage they have, the more energy they can store in the same volume. The other component is the microprocessor that does the work. The voltages on microprocessors have been going down over the years from 5 volts to 3.3 to 2.5 to 1.8 to 1.2 to around 1 volt today. The lower the voltage, the less energy it consumes, so the battery will last longer. But the problem is you can't apply 3.7 volts to a 1 volt microprocessor. It will burn out. Somehow, you have to get the energy from the battery into a form the microprocessor can use. One of those ways is to use a linear regulator, which in the past was the common way to reduce voltage. Problem is, a linear regulator is just a fancy resistor. In this example, dropping 2.7 volts across the regulator at 1 amp of current would produce 2.7 watts of loss, which becomes heat. That's 2.7 watts wasted for every 1 watt of power doing work, something useful, which is only 27% efficiency. That's where switch mode power supplies come in. Here's an example of a buck regulator circuit. A buck regulator reduces voltage, can change this 3.7 volts to 1 volt that's needed and do it at greater than 90% efficiency. It breaks up the input voltage into pulses, and the inductor and the capacitor smooth it out to a lower average. This allows the energy in the battery to supply the phone all day instead of just a few minutes. The inductor is one of the key components in any switch mode power supply. Buck regulators make up the vast majority of switch mode power supplies that are built. By far, they're the greatest number. You'll find them everywhere. Almost every microprocessor has one or more nearby, and almost everything today has a microprocessor. In this board up on the corner are two inductors that are used for buck regulators. Therefore, it's important to understand how they work, how their characteristics influence the power circuit. Magnetic devices like inductors appear to be simple, just some wire and a core, but poor understanding can lead to poor results, especially when things don't work like in the simulation. To be a good power supply designer, you must understand how all the key components work together and how they interact. Inductors are a key component, and you need to know all the things that influence their performance, and that's what we're going to talk about today. Here are a few key points about inductors that we want to highlight before going into the details. Inductors oppose the change in flow of current. This means current cannot change instantaneously but needs time. However, voltage and polarity can change instantly. Inductors operate exactly the opposite to capacitors, where it takes time to change the voltage, but current can change instantly. In switching circuits, we usually apply some type of DC voltage in the form of a pulse to an inductor, which results in a linear increase in current, which we call magnetizing current. Magnetizing current creates the magnetic field, and that field stores energy. Inductors are only temporary energy storage devices. Unlike a capacitor, which you can charge, remove the energy source, and it will retain its energy for a while, inductors cannot do that. You can store the energy, but only as long as you maintain the field. Then you must use it immediately. Inductors and capacitors are used for voltage and current smoothing in power supplies where they complement each other. A saturated inductor has no inductance to impede the current, so it acts like a piece of wire. We'll have a lot more to say about this later. I need to touch on the system of units we use in magnetics without going into too much detail. This is more for your reference. Here in North America, there are a lot of old literature that's in the CGS system, centimeter gram seconds, whereas the literature from the rest of the world is in SI or MKS system, meter kilogram seconds. You have to understand that the differences between the units if you want to be able to read the magnetics literature. The best practice is to think of magnetic units in the SI system because it's much simpler to understand how the equations work. The difference between them is how permeability is defined. In the SI system, the constant permeability of free space is 4 pi times 10 to the minus 7th, and in the CGS system it is 1. This 4 pi times 10 to the minus 7th does not go away in the CGS units. You'll see it in all the formulas as a magic number like 1.257 or its inverse 0.7957 and in exponents like 10 to the minus 8 and so on. Separating out permeability in equations makes it clearer to see the influences of all the different terms. The main units we're concerned with are flux density B, sometimes called induction, measured in Tesla, and magnetic field intensity H, which is measured in amperes per meter. These respectively stem from total flux measured in Webers, which are volt seconds, and magnetomotive force, F, measured in amperes. You often see ampere terms, but strictly speaking, it's amps. Reluctance is force over total flux. Unfortunately, inductance is the same in both units, measured in henries, which is volts seconds over amperes. I have the conversion factors from CGS to SI on the right side for your convenience. We must work within the law. There are a few laws that govern magnetics, and the first one is the Biot-Savart law, which says that a magnetic field is generated when a current passes through a wire and the field strength is proportional to the amount of current that's flowing through the wire and the distance the field lines are from the source. The greater the radius, the weaker the field. Ampere's law says that the net force around a closed path is equal to the total current passing through the path. On the sketch, we have a red current loop passing through two closed paths. C1 is a single turn, and C2 with 2 turns, which will have twice the force. Faraday's law tells us that the magnitude of the induced magnetomotive force or voltage is proportional to the rate of change of flux. The changing flux going through this loop of wire induces a voltage which is proportional to the rate of change. It's important with Faraday's law to understand that it's the change that induces the voltage and the rate of change that determines the magnitude. If there's no flux change, there will not be any voltage induced. If you have a loop of wire and you move that loop through a magnetic field, or if you have a magnet and move it in and out of the loop, both will change the flux, so it works both ways. But the key point is change, which happens over time. Lenz's law tells us that the induced voltage is of a polarity that tends to drive a current through the loop to counteract the flux that created it, hence the negative sign. This is the basis of why an inductor opposes the change in flow of current. Here I want to define and illustrate a few common core terms. When referring to magnetic cores, we speak of cross-sectional area, A sub c, and mean magnetic path length, small l sub c, or sometimes sub m. In an E-core, as illustrated here, A sub c is the area of the center leg. The outside legs are half this area. Because the flux will split evenly between the halves, the magnetic path length, L sub c, is that of one leg. Magnetically, the two paths are in parallel. Knowing A sub c, we can calculate the flux density, and knowing L sub c, we can calculate field intensity, thus applying the material properties to a specific core shape. This gives us an easy way to compare materials and shapes. In magazines, websites, and even data books, L sub c looks like I sub c because they like to use sans serif fonts where the small l and the capital I are the same character. So you just need to know the context of what they're writing about. However, many Faraday cores have unique shapes, and the cross-sectional areas are not uniform throughout the magnetic path, as shown here by this selection of planar cores. It's possible to calculate the equivalent core area and path length, which are called effective parameters, hence the subscript E. The methods for each core shape are outlined in IEC standard 60205. These are the values listed in datasheets. A note of caution, the datasheets also list A sub min, which is the smallest cross-sectional area in a core shape. For toroids and E-cores, the A min is the same as AE, but other shapes, the A min can be as much as 25% smaller. The worst are EP cores. This means if you use a high flux density and calculated it using AE, then it's quite likely that your core will saturate during use, which will result in unpredictable behavior. For conservative design, use A min for all your flux density calculations. In the theory of magnetism, there are no magnetic unipoles. No matter how much you divide a magnet up, there's always a north and south pole. At the elemental level, these are called magnetic domains. In unmagnetized magnetic materials, which by the way at room temperature are only iron, nickel, and cobalt, the domains are all mixed up in an unordered state, and there's no net magnetism at all. When you apply an external field, the domains start to align themselves to the applied field. As the field intensity increases, the domains align more and more until at some point they're fully aligned. Any further increase in field intensity has no effect. We call this saturation. The BH curve illustrates it. Following the red path from 0, 0, which is the initial or completely unmagnetized state, applying increasing field intensity at first gives a large increase in flux density, but soon the rate slows down to almost nothing at saturation. When the field is decreased, most of the domains return to their random state, but not all, and we are left with a remnant flux, B sub r, at 0 field intensity. In order to remove the remnant flux, you must apply a negative field, H sub c, called coercity. This path traces the BH curve, and we see it as hysteresis. It does not return in the same path that it went out on. That's why the BH curve is often called the hysteresis curve or loop. The area within the curve is the energy used to rotate the domains, which is core loss. it's easy to understand that operating at higher frequencies means traversing this curve more often, which translates into more core loss. Here are some of the terms we use to describe BH curves. First thing to note is that the BH curve is almost always shown going from fully saturated to fully saturated. And except for special applications, cores are not normally used this way. Only a small portion is used, like the blue curve on the right for this unipolar pulse. The main thing to understand is that delta B is always the total flux swing that's used, like peak to peak, whether it's unipolar or bipolar. B is always 1/2 of the total flux swing. Then when we talk about B peak or B max, we're always talking about measuring from 0. And these are the design values, which include DC bias plus AC flux. Note that B peak is not the same as B. Saturation is referred to as B sat and is always the extreme limit. BR remnants, as I explained to you, is what's left over when the field intensity goes to 0, and HC coercity is field strength needed to return the flux density to 0. Let's connect the dots. We see that Faraday's law links voltage with respect to time to total flux. We see that Ampere's law links current to force. And the thing that joins these things together is permeability, which we saw was flux over force. That's a material characteristic, but the material comes to us in the form of a core, which has a shape that determines its cross-sectional area and mean magnetic path length. With these, we can convert total flux to flux density and force into field intensity, which are the core characteristics. The BH curve shows us that this relationship is nonlinear, though we often treat the usable portion of it that way for simplicity. This allows us to have a single number for inductance factor, AL, and to determine energy storage capacity. The final link to inductance is the number of turns, which is a multiplying factor, but again, nonlinear. Now, we can link what's wanted in the circuit, the terminal characteristics, an inductance, and some current, which represents some energy capacity, to a physical realization in a specific material, a core shape, and a number of turns. A simple equivalent circuit of an inductor looks like this. There are 4 components. Inductance is the main element, and the others are losses. The loss elements either divert energy into heat or cause it to bypass the inductance. You have R sub W representing the winding resistance, which is both the DC resistance of the wire and the AC resistance from skin and proximity effects. There's also going to be some parallel capacitance in the winding, which will divert current at high frequencies, and it will ring with the inductance at the self-resonant point. In this flat wire inductor, you can easily see how the turns of wire could be little capacitor plates. Then there's going to be some core loss, which is shown as R sub C, and AC resistance from the core itself in the form of eddy currents. An impedance sweep lets you see all of this in action. At low frequency, the DC resistance is dominant. Then as the frequency increases, the steadily rising slope is from the inductance until it peaks at self-resonance. This is where the phase flips, and from here on out, the device is capacitive. We can broadly classify magnetic materials into 4 types based on how they're made. I've listed them roughly in chronological order. In the first group are laminations and strips, also known as tapes. These are the first materials developed in the late 1800s. They're all conductive thin sheets, limiting the frequency of operation, but they offer good permeabilities, high flux levels, and are very stable over temperature. Silicon iron has the highest flux because it's mostly made of iron, which is the element with the highest saturation flux. Nickel iron was developed later, has very high permeability, and is often processed for specific applications. In the second group are powder cores, which are cores made by pressing together various compositions of elements. These were developed in the early 1900s. You can see that there are many different mixes of iron, nickel, molybdenum, silicon, aluminum, and so on, each optimized for different applications. The magnetic elements have high permeability and are highly conductive, but the powder particles are coated with an insulating material to limit eddy currents, and a binder is used to hold them together. This provides a natural distributed gap, which combined with the high flux levels makes them ideal for inductors with DC bias. The permeabilities are low, they're stable over temperature, and they have a soft roll-off to saturation. In the third group are ceramics, which are the ferrites, first developed in Japan in 1930 and later in the Netherlands in the 1940s. They fall into two main categories with many compositions. Nickel zinc cores have low permeability but very high resistivity, making them ideal for the highest frequencies. Manganese zinc have high permeability but lower resistivity, but still much higher than that of non-ceramic materials. They're the most common core used in switching power supplies. Ferrites are limited by a relatively low saturation flux and variability with temperature, but this is compensated for by their very low cost and the ability to be easily formed into many different and diverse shapes. The last group is amorphous metals, developed in the 1970s, and later in the 1990s, the post-annealed nanocrystalline ribbons, which we're seeing increasing usage today. They have high permeability, reasonably high flux density, and lower losses than silicon steel. Though more costly, they're a popular choice in the medium voltage space where frequencies are in the low tens of kilohertz and for a wide range of common mode filters. Here are some powder core characteristics. I should point out that the popular molded inductors use powder core material pressed around the winding. So whether building or buying inductors, understanding how the material affects the performance of an inductor is one of the keys to proper application. In the first chart, you can see that the permeability rolls off with increasing frequency. The lower the perm, the higher the frequency of operation. The second chart on the right shows permeability rolling off with increasing magnetic field intensity H, which in this chart is amperes per centimeter. At some current level, it begins to saturate the core and the inductance will fall off. The third chart shows how the flux increases with magnetizing force. You'll recognize this as a portion of the VH curve. What's not shown at the top are the lines eventually going horizontal at saturation. There are several important points here. First, core loss can be given in watts per volume, typical for powder and ferrite cores, or watts per mass, typical for steels. The units, when referring to volume, are milliwatts per centimeter cubed, as here, or kilowatts per meter cubed. Luckily, the former is 1/millionth of the latter, so conversion is simple. The next point is that core loss charts are log-log charts, which means things change a lot because it's exponential on both axes. Third, this chart is in CGS units, so you must know your conversion factors. Fourth, the flux is given as peak, even though the charts are created from measurements using sine waves. The lines themselves show that increasing the frequency or increasing the flux density increases the core loss exponentially. We will see the same thing for ferrites in a moment. The second chart shows how stable powder cores are over temperature. Over the entire temperature range, here from -60 to +160 C, there's less than 2.5% total change over the 200-degree swing. Keep this in mind as we go on. Ferrite cores are different. This is a typical table you find in data books on material characteristics. The format and the test conditions are outlined in IEC standard 60401-3 to form a common basis of comparison for users. Often the manufacturers include charts which are optional, and in the next couple of slides I want to show you the link between the table and the charts. For example, the first line in the table is initial permeability, and it tells you how easily a core is magnetized. This arrow points to the exact spot on the graph of this initial permeability chart where the reading comes from. You can see that it varies considerably over the temperature range of -50 to +250 C. This is pretty typical of ferrites. As it gets cold, it goes down, and as it gets hot, it increases. And it's not uncommon to have a bit of a wave in the middle. At the operating temperature, permeability can be more than double what it is at room temperature. Also, note its large tolerance, plus or minus 20%. Initial permeability is measured at diminishingly small magnetizing field, and hence very low flux, whereas amplitude permeability is measured over the full range of flux density. You can see that the permeability peaks around 225 millitesla, and that it shifts with temperature. Flux density in the table is at a specific magnetic field intensity in accordance with the standard. Unfortunately, that puts ferrite very deep into saturation. FarXcube displays their BH curves differently than other manufacturers. You can see along the bottom, the chart ends at 200 amperes per meter, whereas BSAT is defined at 1200 amperes per meter in the standard, which puts it off scale. You can see how far off scale by comparing it to this TDK chart on the right. There's no real information between 250 and 1200. Speaking of scale, FarXcube also splits the horizontal scale, which gives it this funny shape. It's their way of trying to give more detail. The important points are to look at the BH curve to determine the maximum usable flux, which is just below the knee at operating temperature, because the maximum flux density is significantly lower at operating temperature. From this, a general design guideline is to use a Bmax that is 80% of the Bsat at 100 C. The Curie temperature, Tc, is where the ferrite loses all of its permeability. It has the same effect as being fully saturated, no inductance. This is fully reversible. Once the core cools down, permeability is restored. In these charts are core losses at different frequencies and flux levels, which is based on sine waves. Similar to what we saw earlier, this is a log-log graph using B peak and kilowatts per meter cubed per units. The second chart shows that the core loss varies significantly with temperature. The purple line joins the identical condition in both charts. Notice that the chart on the left is best case. Ferrites are designed to have the lowest losses at temperatures usually between 80 and 100 C. They have a very convenient negative temperature coefficient, which keeps the part from going into thermal runaway as long as you stay on the left side of the valley. This chart is complex permeability versus frequency of the material. The solid line represents permeability, which shows the frequency limit of the material, and the dashed line represents the core losses, which increase with frequency. You'll find similar charts for ferrite beads and inductors used for EMI suppression. The last chart shows effective permeability versus magnetizing field intensity. These are gapped cores, and it shows how much magnetizing field intensity can be applied before saturating the core. The larger the gap, the lower the effective permeability, hence less inductance, but the greater the DC bias that can be applied. Here's a page from the TDK catalog that shows you the same thing a little differently in the charts. We noted the difference in BH curves earlier. Here, it's easy to see the knee and the lower saturation level at higher temperature. The interesting feature of these two DC bias charts is that the plots are almost identical, even though one is at 25 C and the other is at 100 C. This clearly illustrates that gapping a ferrite core stabilizes the permeability over temperature, making it almost linear compared to the wavy response we saw in the ungapped core. Where is the energy stored? Imagine the magnetic circuit as an electrical circuit, where the magnetomotive force is like voltage, flux is like current, and reluctance is like resistance. The core is low resistance, and the gap is high resistance, both connected in series. Apply a voltage across the resistors, and the current is the same in each. Therefore, the largest voltage drop will be across the high resistance, which is the gap in our magnetic circuit. It's important to realize that the gap is a physical space, and it needs to be larger to store more energy. Operating at higher frequencies reduces the energy required per cycle, and that's why the inductors can be smaller. When a gap is introduced into the core's magnetic path, the BH curve is skewed, as in this green trace here. That means more magnetizing intensity is required to drive the core to the same flux level. The maximum flux level does not change, only the energy to get there. This increases the energy capacity, which is proportional to the area between the curve and the vertical axis. Skewing the curve increases the area, but at the expense of lower inductance, which is the slope of the curve. When you have a discrete gap, the flux will bulge out around it, and this is called fringing flux. It has two effects. First, the measured inductance will be higher than anticipated, and the formula here will compensate for that if the center core is rectangular. A similar formula exists for round cores. The second effect is that the large magnetic field intensity in the gap will induce eddy currents in the nearby windings, creating a hot spot. That's shown by the red, yellow, green spot in this finite element simulation. I realize it's difficult to see. The gap is on the left, then there are 3 foil turns vertically in the middle, core wraps around the outside. A real-life example is this teardown of an inductor that has an overheated winding at the gap, where you can see the charred tape caused by the hot spot. As we showed at the beginning, buck regulators are used to step down voltages between input and output. They offer good efficiency, few components, low switch stress, low EMI, and are simple. However, they do require high side drive, have no galvanic isolation, and if the switch fails, the input is connected directly to the output. The basic circuit consists of 2 switches, S1 and the diode, an inductor, and an input and output capacitor. When the switch is closed, the current flows through the inductor, building up the magnetic field and storing energy. The current, I sub L, increases linearly. The diode is a reverse bias, so it blocks. The load is supplied primarily by the capacitor. When the switch is open, the inductor wants the current to keep flowing. As the magnetic field starts to collapse, it causes the voltage to switch polarity, and the switch node itself becomes negative. Now the diode can conduct, and the current can continue to flow at a decreasing rate from the inductor, supplying the capacitor and the load. Remember, an inductor's current cannot change instantly. The magnetic field builds up during the on time at a rate determined by the inductance and falls off during the off time. The output is smoothed by the LC filter, which averages the pulsed output. The output voltage is proportional to the duty cycle. The inductor ripple current, that is, how much it goes up and down, is determined by the inductance. The current slope is the voltage across the inductor divided by the inductance as seen in the formula. Therefore, with all other factors changed, the higher the inductance, the lower the slope and the ripple. Lowering the inductance will increase the ripple, and if the inductance is lowered further, at some point the energy will completely be depleted and the current stops. This is called discontinuous mode, which works too, but you need a bigger capacitor. The final choice of inductance is a trade-off between the losses and the size of both the inductor and the capacitor. This slide explains 3 important terms or parameters used with power inductors. I average, I out, IDC, IL are all the same, referring to average current being used by the load. We use this to estimate DC copper losses. In the data sheets, this is rated current. I max and I peak are the average current plus half the peak-to-peak ripple. We use this when determining saturation. In the data sheets, this is called I sat. And delta I, or IR, is the peak-to-peak ripple. This determines the AC losses both in the core and in the winding. When you're trying to get the best efficiency from your converter, you need to know what changes will make a difference with regard to your inductor. In every converter, you're going to have some losses from circuit elements just to make it work. Things like the controller, the resistance from the traces, and so forth. These are things you can't really control and they are the minimum constant losses. Then you're going to have some additional losses from switching and from core losses that depend on the material you select. Here I'm showing in the green line a powdered iron core, and in the blue line a ferrite core, and they'll govern your losses up to a certain point. After that, you're basically going to have copper losses from the windings in the inductor itself. As you increase the current through the resistance, the losses continue to increase regardless of the core. There are two parts to AC losses. One is the core losses, and the other is the skin and proximity losses in the windings, which we will talk about in the transformer session. This chart is showing you measurements from an inductor over a temperature range. You can see that this ferrite core inductor, the AC losses, which are predominantly core losses, are going down, and this is consistent with the curves that we saw earlier. In this other chart, our losses where ripple current is held constant, but the DC bias is increasing for each trace. As we move up the BH curve, we're actually increasing our AC losses, even though the ripple is the same and the DC bias has no core loss. We're operating in a lossier part of the BH curve. The shape of the BH curve of the core materials we saw earlier translate into inductance characteristics. We saw that ferrite cores have a sharp knee in the BH curve, and this translates into a sharp drop of inductance after a critical amount of current is reached. You can think of this chart as the BH curve rotated 90 degrees clockwise. This sharp knee characteristic is called hard saturation. The powder core materials have a gradual decrease of inductance, partially due to the high flux density possible with the iron and partially because of the highly distributed gap. We call this soft saturation. Depending on your application, you might choose one over the other. For example, a converter that's subject to current surges would be better off with a powder core to maintain inductance under all conditions, whereas an application where the current demand is steady at high frequencies would benefit from a smaller ferrite core. How is saturation current defined? It is the DC bias current that causes the inductance to drop by some percentage from the inductance with no DC current. The percentage drop varies from one manufacturer to another, and even between different types or series from the same manufacturer. The typical range is 10 to 30%. This puts you on different spots along the curve depending on what core material used for the inductor. You can be on the point of falling off a cliff or conservatively far from trouble. Let me illustrate. I'm going to show you the relationship between a typical inductance versus current chart from a data sheet to current waveforms on the same inductor in a buck regulator as the current increases. The converter has an inductor with a ferrite core. The arrow on the chart indicates the peak current. In the scope captures, the green trace is the inductor current, AC coupled, so we don't see the DC portion, only the current ripple. The magenta trace is output voltage noise, and the blue is the gate drive signal. Here we're operating before the knee, and the current ramp is linear. A little closer to the knee, and all is well. Between each slide, I'm showing the current increases by the same amount, 100 milliamps. We're at the knee, and you can start to see that the rising current slope is developing a curve. We're in spec, but leaving the safe operating area. I should tell you that this inductor has a saturation current spec of 1.7 amps. In this slide, the curvature of the current waveform is very clear now. The converter is still in control. The ripple is exceeding the design limit of 0.4 amps. The noise is slightly increased. This test is at room temperature, and from what we've learned, the saturation point will shift as temperature increases. This is the real danger of working too close to the limits, plus there are always tolerances. Here we're operating just past the spec saturation current. This is the danger after the knee. A small horizontal change causes a large vertical change. The current waveform is getting more and more curved as it's on the verge of going vertical. The ripple current is now 600 milliamps peak to peak. Noise has increased. This might be okay under a worst case condition, but you don't want to be near here under normal operating conditions. And finally, pushing it further, it puts us well into the danger zone. The load increased 100 milliamps, but the ripple current is now at 900 milliamps peak to peak, an increase of 300 milliamps from the last slide. Although the controller is still in control, it's just hanging on. One last point about saturation. You'll recall earlier in the material characteristic curves how the saturation levels decrease with temperature. This chart of ISAT versus temperature for this ferrite core inductor pretty dramatically shows you how temperature alone affects the usable current of an inductor. From a usable current of half an amp at 20 C to only half that value at 140 C. Your application may not see 120 C range, but it makes the point. On the other hand, powder core materials have a much flatter temperature characteristic. The difference is that you can get more inductance for the same volume from a ferrite. Each material has its advantages. The rated current is the DC current that will cause a specific temperature rise, typically 40 degrees C in an inductor in still air. It's not related to the saturation current. Its purpose is to indicate the thermal dissipation capacity. DC current is used because it's simple and repeatable. There are too many possible variables if AC was used. The rating is very dependent on how the inductor is mounted. There is an IEC standard, 62024-2, that provides a common basis for testing. However, manufacturers have been slow to adopt it, preferring instead to use their own methods, which includes some going so far as to attach surface mount components to copper bus bars to get the greatest heat sinking, thus the highest rated current. It can be a game of spectrum-ship, so be very careful to read the fine print. That said, you will find two situations between rated current and saturation current. The first, illustrated here, is where the rated current is about 3.5 amps, but the saturation current is 6.5 amps. That means the inductor is thermally limited by the losses, usually winding losses, and you can only use it to the thermal limit rather than its saturation limit. If you can provide better cooling or tolerate more temperature rise, you can use a higher current without fear of saturation. The second situation is the opposite. The saturation current here is about 2.5 amps, is reached before the thermal limit, which is 3.5 amps. In both cases, you must use whichever is lower. In the ideal, perfectly balanced inductor, the two values would be the same, and those do exist. Now that you know how an inductor works and the various influences on the performance, you're ready to gather requirements. Before you can select an inductor, you need to know your inductance, or at least your input-output voltages. You need to know the load current and the ripple current ratio, that is, what percentage of the load current can be ripple, your peak current, your allowable temperature rise, do you need hard or soft saturation, frequency and duty cycle, and do you need shielding, and what type of mounting you want. With that information, you can turn to Red Expert, which is Worth Electronics' online inductor selector tool, where you simply enter a few of those parameters for your converter on the left side, and it will calculate the inductance you need and presents you with the most suitable inductors from amongst thousands available. It calculates the performance and all the AC and DC losses under your conditions, and it allows you to sort on any column in the table. Then you can easily select a few and compare them to each other on the charts. Then best of all, a couple more clicks and free samples are on their way. We now come to a point where there appears to be a simple fork in the road. Cores with one winding and cores with two windings. We know the former is an inductor, but the two winding fork gets messy, so we need some definitions. One definition of an inductor is a magnetic device that impedes the change in flow of current by storing and releasing energy from its magnetic field. The definition for a coupled inductor can be a little confusing because people take great liberties with it. One good definition is that a coupled inductor is an inductor with two or more windings on the same core which take advantage of the magnetic coupling to influence the behavior of the other windings. The key point is that by combining individual inductors on the same core, there's some advantage, some synergy. I'll show you a couple examples next. And finally, a transformer may have two or more windings on the same core, but it's a different device. A transformer never stores energy. It transmits energy instantaneously through the magnetic field and provides galvanic isolation. That's not a coupled inductor. The most recognizable coupled inductor is the common mode choke. The two-winding version is easiest to understand, but the principle extends to more windings. The windings are wound in the same direction, and for input chokes, they're separated to provide physical isolation from each other, since they carry the input voltage potential between them, and safety standards require separation. There are two types of currents that flow through. The main current, which sets the wire side, is differential, shown in brown here. Current flowing in one wire and out on the other wire. They create magnetic fluxes that cancel in the core, and there's no danger of core saturation. The other current is common mode, shown in green. These are currents flowing in the same direction on both wires, whose return path is through ground somewhere else. This is EMI, and we want to impede it with inductance. The flux from these currents adds, increasing the effect. We want to use a high permeability core for the most inductance with the smallest size and the fewest number of turns to keep the self-capacitance low, because at high frequency, the capacitance is a bypass. High permeability cores are very sensitive to DC bias, so without the flux cancellation of the differential currents, we could not use them, and we'd have to use large individual inductors to accomplish the same thing. Therefore, the coupling brings many advantages. Another example is the Flyback Converter, which uses two separate inductors, but can also use one inductor with two windings. The advantage is if you combine them, aside from being one component instead of two, the inductances interact with each other, and you actually get a much lower ripple, about 1/4. The topology works either way. The other advantage is that you can use leakage inductance to steer the ripple current to the input or the output. The interaction between the two windings actually makes it better, so you can have lower ripple, or you can have your inductor smaller by using a coupled inductor. And finally, the Flyback Converter. This is an isolated version of a buck-boost converter that uses what appears to be, and what we often call, a transformer. But under examination, this is not a transformer at all, but really two inductors sharing a common core. Now, this sounds suspiciously like a coupled inductor, but hang on. In the circuit, they operate separately at different times and do not influence each other. Because they have mutual flux, the inductances and currents are proportional to each other, just like a transformer. Also, because the input and output windings are separate, they have the transformer property of galvanic isolation. No inductor has galvanic isolation, and transformers do not store energy, and they transfer power instantaneously. This device stores energy using one winding during the first period when the switch is closed, while the load is supplied by the capacitor alone. It then delivers energy during the second period with the other winding when the switch is open. Voltages exist on both windings at the same time, but current only flows in one circuit. That's what makes it unique. It's a kind of crossover device between a transformer and an inductor. You might call it a transductor, but that name's already taken for another magnetic device. Two proposed names are energy storage transformer or transformer choke. Neither is caught on, but they are sometimes used in an attempt to be more precise. Regardless, it belongs in this session, and it provides a segue to our next webinar, which is about transformers. In summary, inductors play a key role in power conversion as energy storage devices for efficient power transfer. You need to know how to properly rate them for your operating conditions because there are thousands to choose from for every application. There are plenty of application notes, reference designs, data sheets, selectors, simulators, and more available online. But the best place to start is where everything is together in one spot, and that's at we-online.com/redexpert.
This podcast was taken from a recent Worth Electronic webinar. To view the materials and replay the webinar on demand, simply click the link attached in this podcast. You are listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists. We're going to shine a light on interesting topics. We have energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.